Welcome back everybody to another lecture of second year physical chemistry, and today we will deal with the activity, which is real-world chemical potential. What will be covered and why? In the previous lecture everything was derived from ideal behavior, both the gas and the solution. But what if things are not ideal? What then? That is what we'll be dealing with today. What will you need? The previous lectures on chemical potential of ideal solvents and solutions you will need. In terms of mathematics, you need to remind yourself of your log rules. And from Atkins's physical chemistry, you'll need to go to the section on simple mixtures, dealing with activities. So what is the activity? So here's the first equation. It's the chemical potential for an ideal solvent. It is the chemical potential for liquid is equal to its pure state, denoted by star. Remember, this is where we have decided to define it relative to its saturation vapor pressure, plus RT log mole fraction. What if the solvent is not ideal, which is pretty much most solvents in the real world? What we do is we cheat or we fudge this equation, and we state it as the following. The chemical potential of a liquid is equal to that of the pure state plus RT log A, where I've colored it in with a red, A. The mole fraction gets replaced with the term activity. It's denoted as A. So if we recall from the previous lecture, the mole fraction for an ideal solvent is equal to the pressure on its saturation pressure. So what we now do is we just recognize that the activity is just the pressure on the saturation pressure. Now, why do we do the above? We do this so that we avoid rederiving everything we've done so far for any new material. Instead, we keep a common equation and lump all real behavior into one parameter. Now, if you want to see what I mean by keeping the same equation, have a go at trying to derive the chemical potential for a van der Waals gas. You will quickly find out that it is not simple at all. So, let's keep an equation that is simple and understandable, but we just tweak it for the real world. So this brings us to a bit of a joke. Remember kids, science is not about truth, it's all lies to children. The lies just get more sophisticated the further we go. I hope you see the point what I'm saying here. Science is about approximations. And we're trying to get towards the truth, but we have to always add new additional corrections. So the activity definition, let's keep going. It is easy to get the activity for a solvent. All we have to do is measure its vapor pressure and compare it to its pure state. If the vapor pressure behavior follows Rayleigh's law, the activity just equals the mole fraction. If it does not, we have a non-ideal solvent. For ideal dilute solutions, ideal behavior for solvents and solutes approach the ideal as the solute amount becomes small. So we have the following we can conclude, which is that the activity of a solvent becomes that or approaches that of the mole fraction of the solvent as the mole fraction of the solvent approaches 1. And the inverse you can see for the solute. The activity of the solute approaches that of the mole fraction of the solute as the mole fraction of the solute approaches 0. So let's just discuss some more behavior of solvent activity. From the previous slide, we have the activity of the solvent and its conditions. What we would like to do, love to do in fact, is to keep the mole fraction as a quantity in our chemical potential equation. So what we can do is using the above, we can define a new parameter called the activity coefficient. And it's very simply defined by saying that the activity of a solvent is equal to gamma, the activity coefficient of the solvent, times its mole fraction. Where we just recognize that this activity parameter, gamma solvent, has to approach 1 as the mole fraction of the solvent approaches 1. So basically, we can rewrite the chemical potential, which you can see here below, and you can, using your log rules, split up the activity component into two different sections, which is the ideal part, as you can see out here at the far right, RT log mole fraction, that's your ideal part, and the real part, or the non-ideal part, which is RT log gamma. So, by measuring the vapor pressure and comparing to the mole fraction, we can get the coefficient. Now you can pretty much do the same for a solute, but we have to remember that the activity coefficient for a solute approaches 1 as the mole fraction goes to 0. So it's the opposite case for a solute as opposed to a solvent. Again, you can rewrite the chemical potential for your solute in exactly the same manner and split things up into the real and the ideal components. Just note that the standard chemical potential mu circle is not the same for a pure state of the solvent because it accounts for Henry's law. So if you want to remind yourself about Henry's law, go and see the previous lecture. Alright, the key takeaway. Activity captures non-ideal behavior, and it's formally defined as activity equals the pressure you measure divided by the saturation pressure. Activity coefficients are different for solvents and solutes, and the activity coefficient is defined as gamma equals A on X, where X is the mole fraction. Now for the quiz. There are 4 questions. Some of them are multiple choice, some of them are numeric. Let's start with question 1. You have a solvent with a saturation vapor pressure of 24 millibar. The solvent contains 50% of the molar amount in the solution, and the pressure measured is 20 millibar for the solvent. Can you determine the chemical potential? Yes or no? Question 2. Do we have an ideal dilute, or a non-ideal solvent? And you've got 3 options. A, ideal, B, ideal dilute, or C, non-ideal. Question 3. Determine the activity from question 1. And question 4, determine the activity coefficient from question 1. And note, it may be equal to 1.